Hello everyone, on today's class we're going to be covering some examples on the different modes of heat transfer. So let's go ahead and start with our first example. Let's read the problem statement. An electrical heater embedded in a long cylinder of diameter 30 millimeter. Air at 23 Celsius blows over the cylinder. The surface temperature is 90 Celsius. The heater puts out 400 watts per meter. What is H? So before we start solving, the first step you want to do is draw a schematic of the problem and write down your givens in that schematic. So we have a cylinder, okay. Inside the cylinder, there's an electrical heater that's embedded inside the cylinder. Okay. The surface temperature is 90 Celsius. The air blowing at the cylinder has a temperature of 23, so the temperature of the surrounding T infinity is 23 Celsius. And we're looking for H. So this is your cylinder. That here is your heater. Okay. Now the heater puts out 400 watts per meter. That is your Q. But what type of Q? So we have Q, which has units of watts. We have Q prime, has units of watts per meter. And Q double prime have units of watts per meter squared. Okay, so in this one, Q equals Q. Okay, let me write it down here. Therefore, Q equals Q prime times L. Okay, this is going to be, this has units of watts. This has units of watts per meter times meter, which will cancel out and be, both sides will have the same unit. Okay, whereas Q also equals Q prime times area. So for this example, since we're given the heat flow or the heat transfer in watts per meter, we're going to be using Q prime. Okay, so from the problem statement, we can identify that we're working with a convection. Why? Because there's a fluid, air, with a surface that's emitting heat. Therefore, we're working with convection. Okay? Therefore, we'll start solving by using Newton's law of cooling, which is Q equals AH times Ts minus T infinity. Oh, sorry. Yes, that's correct. Newton's law of cooling. Now, we have Q prime. We're given Q prime equals 400 watts per meter. Okay? So, in order to solve for Q, therefore Q prime equals Q over L, giving us Q prime equals AH Ts minus T infinity divided by L. Now the area of the cylinder is pi dl. Okay, you can substitute that into the equation here, and we'll get q prime equals pi dl times h times ts minus t infinity divided by L. The L's can cancel. Solving for H will equal Q prime divided by pi d Ts minus T infinity. Okay. Now plugging in the numbers. Our Q prime is 400. Our T infinity is 23. T surface is 90. Am I missing anything else? Nope. Oh, diameter. Diameter of the cylinder, 30 millimeter. Okay. So that'll be 400 watt per meter divided by pi. The diameter should be in meters. Okay, times Ts, which is 90 minus 23. Therefore H equals 63 watts per meter squared Kelvin. Now you might say, hey, how's the units Kelvin when we use Celsius in the equation? Well, here we're only using the difference of temperature. So for Kelvin and Celsius, it would be the same. So it wouldn't matter as much. But if you want, you can always change it into Kelvins or leave them in Celsius. It won't really matter because it's a difference of temperature. Okay? But the key part of this example is knowing which Q you're working with based on the units you have. If you have watts, it's normal heat flow. If you have watts per meter, it's Q prime, which is heat flow per length. And of course, flux, it's watts per unit area. And in order to find Q, you need to, for example, this one here, Q prime, Q, the normal Q will equal Q prime times L. Okay? Nope, divided by L. Divided by L. Q prime. Nope. Q prime equals Q over L. I think I'm overcomplicating it here. Q double prime equals normal Q over area. Okay? And that's it for this example. Let's move on to the next one. Second example, let's go ahead and read the problem statement. A cubicle freezer compartment is 2 meters on a side, with the bottom being perfectly insulated. Thermal conductivity K of the material, which is styrofoam in this example, is given to be 0.03 watt per meter Kelvin. Heat load is given, your heat transfer. The inside temperature and outside temperatures are given. Find the insulation thickness. So, as I said, before you start solving anything, draw a schematic. Write down your givens in that schematic. So, let's draw a cubicle freezer. Okay. Something simple like that. Okay. Now, The bottom being perfectly insulated, meaning that the bottom there's no heat transfer. So we can eliminate that there's any heat transfer from the bottom part, the bottom side. Okay? K is given, heat load is given, temperature inside. Oh, the dimensions of the freezer is 2 meters on each side. So 2 meters on width, 2 meters on length, 2 meters on height. Okay? Let's assume the temperature inside is the same anywhere. It's the same at the walls, it's the same at the center. So T inside temperature equals -10 Celsius, and the outside temperature equals 35 Celsius. And we want to find the insulation thickness. We want to see the thickness of the freezer walls that heat is being transferred from the inside to in. Heat always transfers from hot to cold. Okay? So that is a conduction heat transfer, because heat is transferred through the material, styrofoam wall or border or wall. We'll just use wall. Okay, the freezer wall. Okay, so let's write down Fourier's conduction law, which states that Q equals Ka. Since it's one dimension, in chapter 1 we'll be using delta T instead of differential of T over L. Okay? Now, let's solve for L in that equation, which is the thickness that we want. We're looking for L. So, Q divided by Ka over delta T equals 1 over L. Therefore, L equals Ka delta T over Q. Let's go ahead and sub in the numbers. L equals your K, temperatures, K is 0.03 watt per meter Kelvin, times the area. The area of the walls that heat is transferring through are 5 walls. Well, we won't include the bottom one because there's no heat transfer through the bottom one as stated in the problem statement. So there's 1, 2, 3, 4, 5. The top one is also, we're also considering that one. So 5 walls of the freezer walls, 5 times 2 by 2, which is the cross-section area of the wall. So the area is the cross-sectional area of the wall, and there's 5 of them. Okay, times delta T, which is T outside minus temperature of the inside. Okay, delta T is T2 minus T1, which is outside minus inside, divided by Q, which is 500 watts. Again, since this is a change in temperature, it doesn't have to be in Kelvin. It could be in Celsius or Kelvin. So that won't make a big difference because it's a change in temperature. It's a difference in temperature. Therefore, L equals 0.054 meters, which is 5.4 centimeters. Okay, let's go on to the third example. Read the problem statement, make a schematic, write the givens on the schematic. So a spherical instrumentation package with a diameter of 100 millimeters with emissivity of 0.23 in a large space. Take this into consideration. Large space chamber whose walls are at 77 Kelvin. The outside temperature is 40. How much is the power being dissipated by the package? So power is measured in watts. What also is measured in watts is the heat rate. So we're looking for Q. So since we're working with a large space, a small object in a large space, we'll be using Stephen-Boltzmann's equation that applies to small objects in a large space, as shown in the graph here. This is your Stephen-Boltzmann's constant. Okay, for your T surrounding, it is 77 Kelvin. Okay. The outside temperature of the package, T surface, is 40 Celsius. Let's change that into Kelvin. That'll be 313 Kelvin. The emissivity is given 0.23. And you just need to plug it into the equation. Therefore, Q equals 0.23 times the Stephen-Boltzmann's constant, 5.67, times 10 to the power of -8, times 313 minus 77. For your power or your heat flow will equal to 3.07 times 10 to the power -6, which does not make sense. And that is because I was solving for flux instead of solving for Q. So what I needed to do, let's erase this and start over. So what I needed to do was solve for Q. Okay. Solve for Q, and Q double prime has the units of watts per meter squared. Therefore, Q equals Q double prime times area. Therefore, I need to use this formula but add an area to it. Times it by the area of the sphere that's emitting the heat. Okay, so this is the emissivity of the object emitting the heat, and this is the surface temperature, and the area is the area of the body emitting the heat. Therefore, Q equals emissivity times Stephen-Boltz's constant times area of a sphere, which is pi d squared. Let me double check that. Pi d squared. Yeah, that's correct. Pi d squared times TS4 minus T surrounding to the power of 4. Yeah, guys, if your final answer doesn't make sense, look back at your steps, and that's the benefit of like solving step by step is so you can track your steps and see where you went wrong. So that final answer was definitely did not make sense. So I had to look back and see what the problem was. And the problem was that I didn't times the equation with by area, and I was solving for flux thinking that I was solving for the heat rate, which is just Q. Okay, so let's go ahead and substitute our numbers. Q equals 0.23. Yep. Times the Stephen Bolt's constant, 5.67 times 10 to the power of negative 8 times pi times the diameter. Let me double check the diameter. Yep, 100 millimeters, which is 0.1 meter squared, times TS being 77. Nope. TS is the temperature of the surface of the body emitting the heat, which is 40 Celsius and 313 Kelvin. 313 Kelvin to the power of 4 minus 77 to the power of 4. Q equals 3.91 watts. And that's the amount of power the system is being dissipated by the package. Okay. That's it for this class. Next class, we'll cover energy balances. See you then.